My name is Abasi, Cyprian, Yameso. I'm a researcher in the Department of Chemistry of the DOT. I came to this university a little more than a year ago with the intent to extend my research area, where I have collaborated with my line manager and some other researchers back home in my university. And that extension is what I'm presenting this morning. And as you can see, it's titled Ternary Layered Double Hydroxides for removal of toxic metals from aqueous solution. I want to say that our work is a pollution-related work. Though it's simulated work, but it's our hope that when we have the time, we'll be able to apply it in real time.
No, this side.
Sorry?
What is it?
It's not the right one.
Let's take it out.
Okay, so I'll be taking us through the items on the outline here, the introduction in this talk, the synthesis protocol, since we are talking about a material which we'll use for the removal of ions from aqueous solution. Remember, I said that this work is a simulated study. So we just carry it out in the laboratory, and thereafter we can now apply it in real time by taking water samples, maybe from effluents or river portions. So these are the things I'm going to talk about this morning: the characterization, the experiments we did, and then the removal proper by the materials that we synthesize, that is the layered double hydroxides, then the summary of the findings and the conclusion, and then the articles that we are writing based on this work and some other work that we did. The last speaker was talking about water treatment, and so we know that water pollution is not a new story all over the world. Everywhere we know that water pollution is there, and it affects everybody. It's for the low, for the high, it affects everybody. In fact, somebody has already said that metals have two faces. One face, it is a servant. Another face, it is a silent killer. And then another face, one face is a friend, another face is a foe. So we need materials to actually remediate, because just as our professor said, you cannot actually remove everything, but at least you bring the level down to a manageable level, a tolerable level. So materials are actually needed to take this unfriendly face of the metals via remediation or removal. So coming to what we did, that is the layered double hydroxides. Actually, they are clays, and they are anionic clays, and The layered double hydroxides, they're actually made up of metal hydroxide sheets. And in between these sheets, in 2 dimensions, they have anions and then water molecules in between. The formula that is used for them is as shown there. This as a formula, that is, we have a divalent metal ion and then a trivalent metal ion. As the name implies, you can see the OH there, a double hydroxide, 2 OH group, and then we have the anion there, and then we have also the water. If you look at the skin there, you can see the sheets. Here is one layer, and this is another layer, and in between these layers, we have the water as well as the anions that are in there. This is another illustration of what we are actually talking about. Now, one thing about these materials is that their composition can be varied. They are tunable. That means we can replace, we can substitute the metal ions. At the same time, the anions that are in between the sheets can be exchanged. Other ions can be brought in, and because of that, we have a wide range of products that can come out from this material. Actually, the substitution and the variation of the composition of these materials actually promotes charge density. That is, the charge density on these layers, they are increased as you bring in new metal ions. And because of the surface charge on these sheets, as well as the charge in the interlayer, where you have the anions, it confers upon these particular materials some sorption properties. And that's why our interest is now laid on using it to remove the metal ions. Part of our motivation, as I said, we have been doing some work on binary layered double hydroxide. That means they have just 2 metals in the structure of that material. Derivatives also have been made, and we thought it wise to move to, as I said. So the number of the metal ions, as I said it, we can increase it. I think now, all right. So when we have a layered double hydroxide, that is LDH containing 3 metal ions, we call it ternary layered double hydroxide. And so these ternary LDHs, they are proposed to show better removal properties because of increased element compositions and a higher charge density. The material that we used, the first one, is cobalt, zinc, aluminum layered double hydroxide. And it's not been used for liquid phase adsorption, and that's why we decided to use that. This is a synthesis protocol that we used. We used the nitrate of those metals, and then the compound that will provide the anion, that is this, as well as this one that also provides the hydroxide. And in the scheme here, you can see we mix the metal nitrate together with the basic solution by slow addition dropwise at controlled temperature and pH. And after that, we allow it to age for some time. Sometimes we age for 10 hours, 12 hours, depending on what we have chosen. The slurry will be formed, and then it will be centrifuged. And then we wash it, we will dry it, and then the product is formed. So actually know if we have formed it, we use some characterization. These are some of the characterization methods we used to actually determine the formation of our material. Then We also did the removal by adsorption experiments with respect to some physicochemical parameters which are already there. These are pictures of our setup. We had to improvise. Actually, there were some things we didn't have, and so we improvised. And at the end, we were able to come up with these 4 products that are shown there. For the first one which we did, the synthesis materials, they are the ones that we are shown. The nitrates were used, and then the synthesis method also by cold precipitation. Then the batch adsorption method, which is the method actually we use to remove the metal ions, we use those operating variables. These are the characterization results, the FTIR, and then the XRD, the TGA, DTA analysis, and then the nitrogen sumption isotope. This is the same results.
We're running out of time.
Okay, thank you. This is the EDS. As you can see here, sorry, you can see that the lead, this is before the adsorption, and this is after the adsorption, and you can see here, the lead was actually what absorbed by the material. These are some of the adsorption experimental results we had. These are other results on pH and then the concentration, that's for the time. And then these are another 3 set of the ternary layer double hydroxides that we prepared. These are some of the results, characterization, and then this one is the TGA, DTA. We couldn't actually do the other ones we did for the first one. These are some of the adsorption results.
It's over.
Thank you.